Welcome to Unit 4, and in this section we will be solving and graphing inequalities on a number line. By the end of this lesson, you'll be able to graph and solve inequalities. An inequality is a relation which makes a non-equal comparison between two numbers or other mathematical expressions. So basically, an inequality compares any two values and shows that one value is less than, greater than, or equal to the value on the other side of the equation. So a comparison between two numbers might be such that we're comparing 3 and 5, and that 5 is greater than 3, or 3 is less than 5. It also can be with mathematical expressions, which we'll do later, such as a value plus 2 may be greater than or equal to 10. What values of x makes that true? The four inequality signs that we'll be dealing with this lesson is less than, greater than, less than or equal to, greater than or equal to. We also have not equal to, but we will not be working with that symbol in this lesson. So our three steps that we'll be using to graph inequalities on a number line is that we are going to isolate the variable. We're going to treat that inequality like an equal sign while we isolate that variable. If it's less than or greater than, we will put an open circle on that point. And if it's less than or equal to or greater than or equal to, we'll put a closed circle on the point. And then we can use a test point or read our inequality and shade it correctly left or right. It will always shade on the left as long as the inequality is pointing to the unknown. So here we can see that x is on the less than side, less than or equal side, and if it's on the right side of the inequality, if you read it from the variable, you're saying x is less than the value, or x is less than or equal to the value. Similarly, the same thing for the right. We'll shade to the right if the variable is being eaten, because that's saying all the solutions that are bigger than or equal to the other expression. Please highlight this most important phrase in your note packet for section 4.1. We treat the inequality like an equal sign when we isolate the variable, except when we multiply or divide by a negative. We have to switch the inequality. So if it's less than, it then becomes greater than. Similarly, if it's greater than or equal to, it's going to become less than or equal to. You have to flip the sign when you multiply or divide by a negative while you're isolating the variable. Let's begin here. We're going to graph the solution set, and that means finding all the values of x that make the inequality true. If we read this, x is on the pointy side of that symbol, meaning x is less than or equal to 5. So if this was an equal sign, and it said x is 5, we're now changing it to is less than or equal to 5. So let's put 5 on our number line. And if you want to put the other numbers, one before, a couple before, or a couple after, that's great. Well, 5 is that point that we need to decide, is it greater than 5, less than 5, less than or equal to, greater than or equal to, equal to? Well, if it was just equal to, we would graph the solution as just 5. But that's not what it's saying. We're saying all the values that are less than or equal to 5. And that means that 5 is a solution. So we have to use a closed circle. And then we need all the values that are less than 5, and that would be shading it to the left. You can always use test points. Every point this side of 5 makes the inequality true. So let's grab a point. Let's say 3. Is 3 less than or equal to 5? Yes, it is. 0 is less than or equal to 5, and that's part of the solution set. Negative numbers, continuing negatively, so negative 8 is less than or equal to 5. All those are true. And everything not shaded means it's not a solution. So let's pick any value up there. Let's say 10. Let's plug it in for 10. Is 10 less than or equal to 5? No, it is not. So that's a good thing it's not shaded. And the last thing is 5. Is 5 less than or equal to 5? It's the only part of that symbol where it is true, where if that symbol was not there, 5 is not less than 5, we wouldn't include it as part of the solution set. So when it's or equal to, it's definitely a closed circle on that point. Let's keep going here. I do not read this as -1 is less than x, even though that is true. If you read it from the x is actually on the bigger side of that inequality. So we're saying all the values of x, all of the solutions, are greater than, not equal to, but just greater than -1. So that means that we need to graph -1, and x is already isolated for step 1. So then we need to decide, is it open or closed? It's an open circle because -1 is not part of that solution. That is not a true statement here. -1 is not less than -1. It's actually equal to. And without that symbol, it's not a true solution, so therefore it needs to be not shaded. Now, a lot of kids growing up say shade where the arrow points. That is not true unless the x is on the other side. Well, if we flip this inequality, x still has to be on the bigger side of that -1. So we're saying all of the solutions that are greater than -1. That means to the right. And if you want to test a point here, so that would be 0, 1, 2, 3, -2, -3, -4. Anything to this side of it makes it true. So let's pick one and plug it in. Is 2 greater than -1? Yes, it is. If we would have plugged it into the original, -1 is less than 2. Yes, it is. Let's pick one point over here, -4. Is -1 less than -4? Well, the bigger the negative, the smaller the number. So that is not true. So that's good. This side of it, this side of what we shaded, sorry about that, is false. And everything that we shade is true. So all this is false, all this is true. And because of the open circle, that is also false for -1. Now that I reviewed a lot of just graphing an inequality where x is already isolated, now we're going to focus on step 1 where we have to isolate the variable. So we treat that inequality like an equal sign, and we have to get x by itself. So what plus 3 is greater than or equal to -4? We undo addition with subtraction. When we rewrite it, x is greater than or equal to -7. So we need to graph the solution set of that. So I'm going to graph -7. I'm going to graph a couple, or write another couple numbers besides that. All right, so -7, is that part of our solution set? Is it an open or closed circle? And because of the or equal to sign, it is part of the solution set. So we shade it in to show that it's true. And we need all the values that are on the bigger side of -7. So that means all of the values that are greater than or equal to -7. I always like to test a point. 0 is always a fun one to try, and that is to the right of that. Is 0 plus 3 greater than or equal to -4? Substituting it in to check. Let's see here. Is 3 greater than or equal to -4? Yes, it is. So we're good to go there. And let's move on to the next one. All right, step 1 is to isolate x, and we're undoing multiplication, multiplying by -3 by dividing by -3. And not only does it switch the sign of the positive 12 to a negative number, we also have to remember to flip the inequality. If we forget to do that, we're going to shade all the wrong solutions. So let's get our point here, -4, -3, -2, -5, -6. All right, so -4, is it open or closed? Well, -4 is not part of our solution because this is saying all the values that are bigger than or equal, or I'm sorry, bigger than -4. So we're going to shade this to the right. If you had it flipped around to the x being on the left side and -4 on the right side, x is on the bigger side of that symbol. And that means greater than, and maybe that's where you see where it's shading where the arrow goes, but the x has to be on the left side if you do so. All right, let's test a point. I like to test the point 0, and it's up here. So let's plug in 0. 12 is greater than negative 3 times 0. Is that true? Well, yes, 12 is greater than 0. So we shaded the correct side of that point. All right, find the solution and graph it. All right, to isolate x, we need to undo multiplying by 3 and subtracting 7. So we're going to undo subtracting 7 by adding it first. Let's rewrite it. 3 times x is less than or equal to 15. Now we're going to undo multiplication with division. So we get x is less than or equal to 5. So all the values that are less than or equal to 5. So let's get 5 on here. Sorry about the delay. So it'd be 6, 7, 8, 4, 3, 2. All right, so we put an open or closed circle on 5, and because it's or equal to, that means 5 is part of our solution, because 5 is less than or equal to 5. If we would have plugged it into the original, 3 times 5 minus 7, is that less than or equal to 8? Well, 15 minus 7 is less than or equal to 8. Is 8 less than or equal to 8? Yes, it is. It's the equal to case. But we also need to take care of the inequality part. Less than or equal to 5. Let's test the point. 0 ended up being in the solution set here as well, so it should be true if we plug it in. Let's find out. 3 times 0, subtract 7, is that less than or equal to 8? 0 subtract 7, is that less than or equal to 8? Yep. Negative 7 is less than 8. So this is the correct shading. All right, moving on. This time, the variable is on the right side of the inequality. If you want to flip it around, you can. Just be careful that 14 is on the greater side and the expression 2x plus 9 is on the left side, or is on the less than side. Sorry about that. So now we need to undo multiplying by 2 and adding 9. So we're going to undo addition with subtraction first, because we're undoing the order of operations when we solve. And let's simplify that to 5 is greater than 2 times x. Now to undo that multiplying by 2 to isolate, we're going to divide. So x is technically less than, because I'm reading it from the variable, x is less than 5 halves, or 2.5. All right, let's graph this. Well, 2.5, I'm not going to put that on the number line. I'm going to put 2 and 3, and I'll number a couple more tick marks. And so 2.5 is in the middle of 2 and 3. So is that an open or closed circle here? Well, it's not including the 2.5 because it's not the equal to case. So I'm going to leave it an open circle. All right, now x is not greater than, x is on the pointy side, so x is less than 2.5. That means we're going to shade to the left. This time I'm going to pick a different point because I keep picking 0 and it happens to be on the true one. Let's pick a number up here where it's not shaded. So let's pick 6, 7. Let's pick 7. If I substitute that into my original, just double checking to see if I shaded correctly. 2 times 7 is 14 plus 9, so 23. 14 is definitely not bigger than 23. This was supposed to be false because it was not shaded. Everything to this side of 2.5 would make it true if you substituted it in. Now we have variables on each side. Well, a lot of kids will subtract 15 or subtract 7. I like to get my variables all on one side. If you remember, if you multiply or divide by a negative, we're going to have to flip that inequality. And a lot of times we can forget to do that. So what I like to do is I like to make my x's positive whenever possible. So instead of adding 2x to move it to the left side, this is going to be a negative. No, thank you. So I'd rather add the 4x and put the x's on the right side. All right, let's rewrite it. 15 is greater than 7 plus 2x. Now we won't have to flip that inequality. All right, now we have to undo the 7 and the 2 to get x by itself. So we're going to undo the addition here with subtraction first, making it 8 is greater than 2x. And then we're going to divide by 2. And reading it from the letter, x is less than 4. All right, so let's graph that. 4, 5, 6, 3, 2. Open, close, or I'm sorry, open or close circle. It's an open circle because it's not or equal to. And x is on the small side, not the bigger side. 4 is bigger than x. That means all the values less than 4. And 0 happens to be a solution again. All right, let's pick a different number. Let's pick 2. If I plug in 2 for x here and here, let's just make sure we shaded correctly. 15 minus 4 times a random solution in the true area that I'm checking. Is that greater than 7 minus 2 times that same value in that shaded area? All right, so 4 times 2 is 8. 15 minus 8 is 7. On this side, 7 minus 4, and that's equal to 3. So is 7 greater than 3? Well, yes, it is. I'm not looking for the equal to case right now. I'm just seeing, is the inequality true? And it is shaded correctly. If you forget to flip the sign by dividing by negative, checking your answers will make a difference and help you catch mistakes. Let's just look at if you would have added the 2x instead, what would have happened? So we would have had 15 subtract 2x, is that greater than 7? And now the x is on the left side, so we need to undo a positive 15 by subtracting 15. I'm left with that negative 2x, be careful, is greater than negative 8. And I'm going to undo multiplication with division. We're going to divide by negative 2. Now that switches all signs, not just the negative to a positive, but the greater than to a less than. And if you look back at your notes that you just wrote, we did shade everything to the left of 4, but would you have remembered to flip that inequality by dividing by the negative? It's up to you. Make good choices, double check your answers, test points. It's true if it's shaded, it's false if it's not. This last example has a couple ways to solve it, if it makes sense to you. So whatever works, I'm going to show a few different ways. So bear with me. If I knew what x was, I would add first and then multiply by negative 3. So now we need to undo that by dividing by negative 3 and then subtracting the 5. So let's see what that would look like. So I'm going to undo multiplying by a sum by dividing. And whatever I do to one side, I do to the other. All right, so I'm left with my sum 5 plus x, and I divided by negative 3. You got to remember to flip that sign. So 33 divided by negative 3 is negative 11. Now we're going to undo the adding 5 by subtracting 5. So all the values that are bigger than or equal to negative 16. All right, let's do it another way. When I was in high school, I definitely distributed. So I would have done negative 3 times 5 and negative 3 times x. And then I would have added the 3x over because I didn't ever want to divide by a negative. But let's just keep it here. So I would add 15 to each side. That negative is still belonging to the x term. So what is that, 48? And now divide by negative 3. And you've got to flip this inequality. And as you can see, we got the same answer. I just want to show you a little trick. So from here, after distributing, what I like to do back in high school is I like to add that 3x to the right side. Now by doing that, I would have to get rid of the 33 now and then the 3. So I would have subtracted 33 and got negative 48 is less than or equal to 3x. Then I would have divided by 3 and I wouldn't have had to flip the sign. If you notice, all of these are the same, even though mine might look different. But if I flip the x and the negative 16. X is on that bigger side, and 16 is still on that pointy side. So all of these have the same answer. We have 16, it's a closed circle, and I'm saying all the values of x that are bigger than or equal to negative 16. If you want to add a couple more things on there, great. Let's just test the point. It looks like 0 is part of our solution set. Let's plug it in and see if it's true. It better be because it's shaded, meaning it's a solution. All right, so I'm going to simplify my parentheses first. 3 times 5, or I'm sorry, 5 plus 0. Negative 3 times 5 is negative 15. And is that less than or equal to 33? Well, sure it is. I always like to review some word problems or applications of inequalities in the real world because the wording can be pretty tricky. So here, Marcus and Jamal are buying groceries for the week. They cannot spend above $90. Express this mathematically. So here we're saying we can't spend above 90. And when kids read above, they think greater than, but it's not in this case. Let's see why. Let's call X the money we're going to spend on groceries. Now, what can those values of the groceries be? Well, they can't be 100 because I can't spend above 90. So I don't want all the values bigger than 90 because that would include that example that I said of 100. So if it can't spend above 90, then that means we have to be less than 90. Can it be equal to? Can I spend above 90 and spend 90? Well, above 90 means like $90 and a penny. That's above 90, but $90 includes 90. So we can spend up to $90, including 90. And I did want to just mention this. This is going to be a little bit intro for tomorrow. We can't spend negative money. So I can only spend above 0. I don't have to spend any money. I might go to the grocery store and not spend anything. That's still not spending above 90. So I would include the equal to case there as well. So this is technically our inequality of this scenario. However, this is the idea of the lesson. Just know that we can't spend negative money when I get there. Well, I guess unless if I use credit, right? But let's just say we had the cash. All right, moving on. In order to make enough money to pay bills, Celia must work at least 42 hours each week. So at least, does that mean less than 42 or greater than 42? Well, let's call H the number of hours. The number of hours Celia must work to pay the bills. Okay, let's play around with those symbols. Hours and 42. Well, if I work less than 42 hours, am I going to have enough money to pay my bills? Here I'm saying at least. So that means that's the smallest I can work. So my number of hours has to be bigger than or equal to 42 hours in order to pay my bills. So that is our inequality. I'm sorry, I forgot we were supposed to sketch this as well. So 42 is a solution of the scenario, as well as any amount of hours above 42. So that would be our number line. For that last one, I can't spend above 90 means I can spend 90, but not above it. So everything less than 90. And tomorrow we're going to have that 0. We're going to graph compound inequalities. So it'd be from 0 to 90 would be the solution. But today we're just sticking with this idea. Oops. This part of it. Our last example, when transporting frozen pizzas, the Screamin' Sicilian truck must be no more than 36 degrees at all times. So express this mathematically, and we're going to graph a sketch. So let's say that 36 degrees. I can't have a temperature more than, no more than. So instead of thinking more than, I can't be that. I have to be less than or equal to, no more than that. So it is including 36 because I can't be more than it, but I can be less than or equal to. So let's say temperature, let's say T represents the temperature of the truck. So the value of the degree cannot be more than 36 degrees. So that has to be less than or equal to 36. Take your time on these. Slow down whenever you have applications. These are just a few of the words that can get you caught off. No more than and at most. Let's think about $5 in your pocket. If you have no more than $5 in your pocket, that means that I can't have more than 5. So that means I have less than or equal to $5. If I have at most $5, that means that 5 is the most it can be. That's also less than or equal to 5. No greater than, that's another one. No greater than would be that case. And there's definitely more, but these are the main ones. Going back to that $5 in your pocket, if you have no less than $5, then you can't have less than it. No less than. Can't have less than it. You have to have greater than or equal to 5. And if you have at least $5, that means you have $5 or more. This could also be no fewer than, and there's other phrases as well, but these are the big ones. Going back to our learning targets, can you now graph inequalities? And can you solve inequalities? And I bet you can do even a little bit more. All right, take care.